Good evening, class, and welcome to Chapter 10, Part 1. As always, please have a periodic table, a calculator, pen, pencils, scratch paper, and your pre-printed notes. So we're going to be talking about Chapter 10 today. We've talked about all sorts of chemical reactions, how to figure out what you get if you mix two different things, what happens when various types of chemicals are mixed. Now we're going to talk about how fast these reactions happen, because the speed of a reaction varies enormously over a full range. We can go from seconds to years for reaction rates. So, for example, the ripening of fruit is a chemical reaction which happens in a matter of days, depending on the type of fruit. The tarnishing of silver is another great example of a chemical reaction, but that happens over the course of months. And of course, humans aging is also a chemical reaction, and that happens over decades. So there's lots of different examples of chemical reactions, and as I said, the rate of a reaction can go from seconds to years and years and years and years. So let's talk about what you have to have in order for a reaction to even happen. I mean, never mind the speed. What do we have to have for the reaction to occur? Well, there are some criteria. The first three conditions that are super important is number one, collision. The reactants have to collide with each other. If there is no collision, there is no reaction. Important condition number two, orientation. The reactants must be properly aligned in order for the bonds to break and new bonds to form. So for example, if you have two molecules, say one like this and one like this, if they're facing this way and they collide, you could get a new product, right? You could get this. However, if your two molecules are facing this way and they collide with each other, you get nothing. So orientation is the direction that the molecules are facing. And in order for a reaction to occur, they must be facing in the correct direction. So they have to collide and they have to be facing the right way. The third and final very important condition is that there must be enough energy. So when the collision happens, they must hit hard enough and with enough force and energy to break the existing bonds and form new ones. So these three conditions are really important. If these three conditions are not met, there will be no reaction at all, and hence no reaction rate. So how do we measure the rate or speed of a reaction? Well, this is measured by measuring the amount of reactant used in a certain period of time or the amount of product formed in a certain period of time. It's just like we measure the speed of our car in miles per second. Well, we measure the rate of a reaction in amount per some unit of time. For example, we've used moles a lot as our amount, so you might be looking at moles per second, or moles per minute, or moles per hour, but you're looking at an amount, a concentration, over a change in time. Reactions that have low activation energies go faster than reactions with high activation energies. Well, what is an activation energy? The activation energy is the amount of energy that must be present in order for the reaction to go. So remember our three conditions? The first was that a collision had to occur. The second was they had to be facing the right way. And the third was that there had to be enough energy in order to break the bonds and to form new ones. Well, that energy is called the activation energy. So if you have a low activation energy, meaning you don't require as much energy, then you're going to go faster than a reaction that requires a high activation energy. For any reaction, we can affect the rate. And there's various ways we can do this. The first is a change in temperature. If you increase the temperature of a reaction, you increase the rate or speed at which it happens. Anybody want to guess why? Well, hopefully you remember that temperature is a measure of kinetic energy, which has to do with the motion of the molecules. The faster or higher the kinetic energy, the faster the molecules move, the more likely they are to collide. So if you have a couple of molecules in a container, and they're moving really slowly along, very slowly, What is the likelihood that they're going to bump into another molecule moving along very slowly? Right? Versus if they're flying around the container super fast, right, they're much more likely to run into each other. So again, at higher temperatures, you increase the kinetic energy, which increases the speed of the molecule, which makes it more likely to collide. So for every 10 degrees Celsius increase in temperature, most reaction rates are looking at roughly double. So if you started out with a speed of 1 mole per minute, and you increase the temperature by 10 degrees Celsius, then you're probably looking at a rate of approximately 2 moles per minute. Right? You're looking at a rate roughly double for every 10 degrees Celsius that you increase the temperature. Okay, how about, let's see here, increase in concentration, right? If you increase the concentration of something, there are more of them. So if you have your beaker, right, if you have just a few molecules, what is the likelihood that they're going to run into each other? Versus if you have tons of molecules all moving around in your container, what is the likelihood that they'll run into each other? Of course, the more molecules there are, the more likely they are to run into each other. So again, an increase in concentration increases the reaction rate. And then finally, there's a third way we can speed this up, and that's by adding something called a catalyst. A catalyst is something that's not used in the reaction, however, it makes the reaction go faster. And it does this by providing an alternative pathway that has a lower activation energy. So remember the third of our conditions, which was that you needed enough energy in order for the reaction to occur? Well, including a catalyst decreases the amount of energy necessary to make your reaction happen. So it's not increasing the likelihood of a collision, right? Instead, it is decreasing the amount of energy necessary for the reaction to go. Okay? And when we do this during the reaction, the catalyst is not used up or consumed because it's not part of the reaction. So there's a nice picture here that shows the activation energy for the uncatalyzed reaction versus the lower activation energy that occurs when you add a catalyst. All right, let's do an example. Example 1. Indicate the effect of each factor listed on the rate of the reaction as increasing, decreasing, or no change. So we have this reaction here. We're mixing carbon monoxide gas and oxygen gas to get carbon dioxide gas. If we increase the temperature, what is going to happen to the rate of the reaction? Well, we said that increasing the temperature increases the kinetic energy of the molecules, which makes them move faster, which should increase the rate. So we're going to say this is increasing. Increasing temperature, increasing rate. What about if we remove carbon monoxide? Now, we said that if you increase the amount, you increase the rate. But in this case, we're removing or decreasing the amount of our stuff. So what do you think would happen to the rate of the reaction? If adding more makes it go faster, wouldn't removing some make it go slower? So that is going to decrease the rate of our reaction. Okay, how about adding a catalyst? A catalyst is something we just talked about. A catalyst is something that decreases the activation energy, which enables the reaction to go faster. So adding a catalyst would increase the rate of the reaction. Okay. How about decreasing the temperature? If increasing the temperature makes the molecules move faster and the reaction go faster, then wouldn't decreasing the temperature make the molecules move slower and therefore the reaction go slower? So decreasing the temperature decreases the rate of reaction. So in most chemical reactions, the reactants are not completely converted to products because when you build up enough product, a reverse reaction can take place in which products collide to form the reactants. So say we start out with H2 and I2, and these guys collide in the right direction, right? And they start making this, HI. Okay, as time goes on and more HI build up, you run into the likelihood that two HI are going to hit each other in the correct orientation and with enough energy that they form an H2 and an I2. So when this happens, we call this a reversible reaction. And it usually happens once enough of the products have built up that they have a likelihood of running into each other. When this happens, again, we call this a reversible reaction. Okay? So a reversible reaction has two possible rates, the rate for the forward reaction and the rate for the reverse reaction, right? How fast are the H2 and I2 colliding to make the two HI, and how fast are two of the HIs colliding to make H2 and I2? So we have two possible speeds. Now, when we start out, we have lots of this and none of this because we haven't made any yet. As time goes on, more and more of these are colliding to make more of this. So the rate is going to start increasing as time goes on, right? You're going to make more and more of this. However, at some point, when you get more of this, you increase the possibility that this reaction here will happen. And so as time goes on, the rate of the reverse reaction begins to speed up because you have more of these in order to make more of those. Okay? At some point, the rate of the forward reaction and the reverse reaction are the same. So at some point, the speed that you are going this way and the speed that you are going this way are the same. We have a special name for this. When the rate of the forward reaction equals the rate of the reverse reaction, we call this equilibrium. Now, I want to say this is really important. Equilibrium has nothing to do with how much stuff you have. Right? So it has nothing to do with how much products you've made or how much reactants you still have left. Equilibrium only has to do with speed. And equilibrium is only achieved when the rate of the forward reaction and the rate of the reverse reaction are equal. This is really important. Okay, so you're going to see a lot of graphs, and so one of the important things here is this is your reaction rate on the y-axis, and you've got your progressive reaction or time down here on the x-axis. Now you start out with lots of products, right? So you've got lots of products up here and no reactants because you haven't made any yet. As time goes on, the amount of your products decreases. And as time goes on in the beginning, the amount of your reactants decreases. The amount of your products begins to increase as you make them. At some point, the amounts level off. When the concentrations level off and you get this flat line, this is your equilibrium. So equilibrium is reached when the lines are flat, but they don't always merge together. Sometimes you use up lots of your reactants and then only have a little bit left, making lots of products. So sometimes the two flat parts of the line are separated. In this type of reaction, you made mostly products, and very little of those products are colliding back with each other to make your reactants again. But however, in both cases, equilibrium has been reached. How can you tell that in both cases you've reached equilibrium? Well, you can tell when the products and reactants reach that flat line, right? It doesn't matter whether they've reached it together or not, even if they're separated. When the line is flat, that means you've reached equilibrium. So once you reach equilibrium, no further changes take place in the concentration, right, or amounts of the reactants and the products. So again, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And they continue on at the same rate. And there are no further changes in the concentrations of the reactants and products. That is how you know you've reached. So how do we determine a numerical value for this? We have something that we call the equilibrium constant. The equilibrium constant is given the symbol Kc. Now, Kc is equal to the concentration of the products raised to the power of their coefficient. Remember that the coefficient is the number that comes just before each molecule in a reaction. So it is the concentration of the products raised to a power based on the coefficient divided by the concentration of the reactants. We've got products here and reactants here. Divided by the concentrations of the reactants also raised to the power of their coefficients. So how would this look for an actual chemical reactant? Our products in the following case are carbon dioxide. So the concentration of the carbon dioxide raised to the power of its coefficient. Now, the first thing you always want to check when you're doing this is to ensure that you have a balanced chemical equation, because you're raising it to the power of their coefficients. If your chemical equation is not balanced, your coefficients will be wrong. So let me just erase these lines real quick here. And let's take a look and see if our equation is balanced. All right, so we have one carbon on the left, one carbon on the right. We have 1, 2, 3 oxygens on the left, 2 on the right. So we are not balanced, are we? What do we need to do in order to balance this guy so we can continue on? Our carbons are fine, right? It's the oxygens that are messed up. So let's see here. We need to make this an even number on the left-hand side, because right now you have 1 oxygen here and 2 oxygens here for a total of 3. In order to make this an even number, you're going to need an even number in front of the carbon monoxide. So let's go with the lowest even number possible. Let's make that a 2. That gives you 2 carbons and now 4 oxygens. If you put a 2 here, you now get 2 carbons and 4 oxygens. That gives you a balanced chemical equation. So now we're going to put the concentration of the products raised to the power of its coefficient. And its coefficient is a 2. So it's going to be the concentration of the carbon dioxide squared divided by the reactants. We have 2 reactants. We have carbon monoxide and we have oxygen gas raised to the power of their coefficients. The coefficient in front of the carbon monoxide is a 2, and the coefficient in front of the oxygen gas is a 1. Anything raised to the 1 power is just itself, so we don't need to actually write the 1 power there. So the equilibrium expression for this reaction, Kc, is equal to the concentration of the carbon dioxide squared divided by the concentration of the carbon monoxide squared times the concentration of the oxygen gas. Let's look at another one. The Kc for the reaction of hydrogen gas and iodine gas is written as follows. H2 gas, 1 mole, plus 1 mole of I2 gas gives 2 mole of HI gas. We saw this particular reaction in a previous slide. So the Kc for this is HI, the concentration, which is written in square brackets, HI squared divided by H2 times I2. So now, using this exact same reaction, we're going to do a couple of examples with numbers in them. So, in an experiment run in a lab, the concentrations of each species are found to be as follows. We have 0.1 molar H2, 0.2 molar I2, and 1.04 molar HI. We want to know what is the Kc for this experiment. So again, our Kc is equal to HI squared divided by H2 times I2. So let's go ahead and put these numbers in. We have 1.04 molar squared divided by 0.10 molar times 0.20 molar. Putting this into our calculators, let's see what we get. So we have 1.04 squared, so 1.04 times 1.04, divided by, now here's where you want to be careful and use parentheses, depending on how you put this in your calculator, 0.10 times 0.20, end parentheses, gives you 54.08 as the Kc value. Now, you have moles times molar on the top divided by molar times molar. So there are no units for this answer because all of our units cancel out. Now you'll notice that this experiment was run 2 more times. So we have this table below with concentrations for experiments 2 and 3. Now they actually show you what the equilibrium constant looks like. They actually calculated it for you in the table. But we're going to do it on our own just to confirm to ourselves that this is true. So in experiment 2, the concentration of the HI was 1.47 molar. So we're going to square that. Divided by 0.20 times 0.20. So this is for the second trial. So 1.47 times 1.47 divided by, parentheses, 0.2 times 0.2, end parentheses, gives me 54.02. Again, the capital M's here, right, the molarities, cancel. Because this is squared. So you have 2 of those and 2 of those. Now, in the third experiment, we got 1.66 molar for the HI squared divided by 0.30 times 0.17. So 1.66 squared divided by 0.30 times 0.17 in parentheses, and I get 54.03. So you can see, now this is experimental data, so of course that's not perfect, but you can see that the Kc value does not change, right? We got 54.08, 54.02, and 54.03. Using correct sig figs, we would round all of those to 54. So the equilibrium constant is tied to a specific reaction at a specific temperature. All of this data was collected at 427 degrees Celsius, and it's all for the exact same reaction. The reaction of hydrogen gas plus iodide gas to give HI gas. So, Kc is tied to a reaction at a specific temperature, and a reaction at a specific temperature can have only one equilibrium constant. So no matter the data, your Kc should always come out the same. So this concludes Chapter 10, Part 1. Thank you so much for listening, and I hope to see you for Chapter 10, Part 2.